So now we have learned what a time series is. We have seen what the components of a time series can possibly be. And we have learned about the additive and multiplicative time series. So moving on to the preliminary analysis of time series, what are the steps in analyzing a time series? Now we are going to do this all in R. So I'm going to describe how to analyze time series in R platform. So the moment you get a time series, first read it into R, store the data as a time series object, and we are going to see how to do this in R pretty soon. Once you have the time series object, you are ready to use the various R algorithms and functions to slice and dice and analyze and forecast the time series data. But first thing first, like the moment you have the time series object, plot your time series, get a plot of the time series, and I'm going to tell you very soon how that helps. Now the plot of the time series, and we have already seen this before, like the plot of the time series, well, it will tell you if the time series is additive or multiplicative. Like we have already seen that just by looking at the plot of a time series, we can say if the fluctuations in the data are roughly constant or the fluctuations are actually fluctuating a lot. So we can tell if the time series is additive or multiplicative. And also we can say, as we have seen in the eBay sales data, if the data has a seasonal component or not. So once we plot the time series and get to know if it's additive or multiplicative, we automatically know the next steps. We have already learned the time series is multiplicative. We need to log transform it to make it additive. And why do we need the additive time series? We need the time series to be additive because all the algorithms are only going to work for additive time series. Once we get the additive time series, we decompose it into the various components to check if the trend, seasonal, and random components are present or not. And once we have checked on the components, we know which modeling technique to use. We can build a model based on that technique and use the model to forecast, and then the last step would be to validate the model and get a robust forecast for the next few months or the next few time points. So the first step, you've got your data, you know it's a time series data. You scan it in. You use the R function scan to read the data in. And as you can see in the slide, scan can either read the data from an URL or it can read the data from a text file or any file, as a matter of fact, saved in your computer. So you read the data and store it into a R vector called sales. We are using the eBay sales data as an example over here. You store the data in sales. Next thing, you need to convert this data into a time series object, and you do that using the R function TS. TS stands for time series. So you feed the sales data into TS, tell TS the frequency of the data. So the eBay data was collected at the end of each month for 12 months, and hence the frequency is 12. So depending on the frequency of your data, you tell TS what the frequency is, and you can also specify the start date of the data. If the start date is January 1st, 1987, issue this command to tell TS that that's what the start date of your time series data is. Store this time series object into sales time series vector. Before we move on, a very crucial point. Like in any modeling technique, there is a minimum amount of data that you need to train your model on. For time series analysis, we at least need 50 data points to build a good model. So this is something you should keep in mind. Now, once we have stored our sales time series object in sales time series vector, we print it out. In the slide, I'm showing how to print out the data just to do a sanity check, just to check if R has read in all the data points, if it has read in the data correctly. So all you need to do is to type in the name of the time series object, and R prints out all the data. And as you can see, we have 1, 2, 3, 4, 5 years of data. So we have a total of 60 data points which is a sufficient number of data points to do our time series analysis. The minimum number of data points that we need is 50, and we have 60 overall. So as I mentioned before, as I already told you, like the moment you have a time series data, the first thing to do is to plot it. So in R, you can plot the time series object using the plot command or the plot function. So you issue the command plot.ts and feed this function the sales time series object, and R plots it for you. So here's how the plot of the sales data looks like. So let's just go back to the previous slide for a moment. Like from this data, can you say if the data is additive or multiplicative? Well, of course you can. Like how do you say that? So what is an additive time series? It's a time series in which with the progress of the level, the fluctuations stay the same. But in our data, if you look at it, like if you go across the time, the peak around 1993 is way higher than the other peaks. So our data is not additive, it is multiplicative. So if the data is multiplicative, what needs to be done next? We need to transform it to make it additive, because all our algorithms are going to work only for the additive time series flavor. To log transform the multiplicative sales data that we had, all we need to do is to pass the sales time series vector into the log function and store it in the log sales time series data. Now that we have transformed, let's plot the data once again and see how it looks like compared to the original data. So on the left panel over here, we have the original time series, which was multiplicative. So the original data has a very high peak around 1993, and hence we can say that the original data was not fluctuating the same way across time. Now after log transformation, you can see that as the level of the time series progresses, as we go across time, the time series data goes up and up, but if you compare the peaks, each of the peaks roughly the same size. So after log transformation, the multiplicative time series is transformed into an additive one. And it is this log sales time series that we are going to use going forward. Let's get introduced to one more type of transformation. Why do we need to learn about more transformation? Well, in most cases, the log transformation would work. It would convert a multiplicative time series into an additive one. That said, transformations are important in time series analysis because it has been proven that transformation increases the accuracy of time series forecasts. So Box-Cox transformation actually is a family of transformation, which means that using this kind of transformation, you can carry out various different kinds of transformation. Now, Box-Cox transformation weighs your data on the basis of a factor lambda. Now, if the lambda is 0, Box-Cox transformation is the same as log transformation. And log transformation is what you need in most cases. But in case if you need other transformation, you can vary this lambda to get other kinds of transformation like square root, etc., etc. And let's see how to transform the Box-Cox way in R. Now, to transform your data the Box-Cox way, you need to use the function boxcox.lambda and feed in your data. If you don't mention anything else, the default value of lambda that will be used is 0.13. And you can store this Box-Cox transformed data into a lam vector. If you want to try out a range of lambda, you can mention to the Box-Cox function the lower and the upper limit of the lambdas. So if you want to check out all the lambdas between -1 and 2, you use a lower bound of -1 and an upper bound of 2, and you may try out several different methods of Box-Cox transformation. I'm not going to get into that. Fit in the data to the function, and the function gives you back the transformed data. Now, to choose which lambda is working the best, you need to look at the x and the y variable that's stored in the lam vector. So the x variable contains all the lambda values that you have tried, all the lambdas between -1 and 2, and the y contains all the transformed data. So if you issue this command lam$x which.max lam$i, this command tells you which lambda has worked the best. So first you need to use the boxcox.lambda, try out a range of lambdas, and then check out like which lambda has worked the best. And then whether you are using the default value of 0.13 or you using the best lambda out of all the lambdas you have tried, you can just go ahead and use the lam vector which contains your transformed data into time series forecasting functions. So ETS is a time series forecasting function which we are going to look at later on. Here all I'm trying to show is that I've passed on the lam vector with the transformed boxcox transformed data into ETS, and we have got a model back in the fit vector. So just a little brief overview of boxcox in case log transformation is not working. Now in case of our sales data, log transformation works pretty well. So we got a data, we plotted it, we saw that the right hand peak is way higher than the rest of the peaks, so we knew that this is not an additive time series. So we log transformed it, and now we are dealing with the log transformed time series. After log transformation, we plotted our log transformed data and compared it against the regional. We saw that the log transformed data has roughly similar fluctuations across time, so our log transformed data is definitely additive, and now we are ready to move on. And so we use a log transformed data and decompose it. So to decompose R, we have already seen how the output from decomposition looks like, but now we are learning how to decompose a time series. To decompose our log transform data, we use the decompose function, and the decomposed time series is stored in the vector on the left. So this is the log sales time series components vector. It has all the components resulting from the decomposition. We plot the decomposed time series, and this is what we get, and we have already seen this output before. So the top panel gives us the trend component, the next panel gives us the seasonal component, and our sales data, if you remember, has a seasonal component. It goes up from October through December. And the bottommost panel gives us the random or the irregular component. So we have decomposed our data, and we have seen that it has all the three components. It has a trend component, it has a seasonal component, and it has a random component. So that is the purpose of decomposing the time series data, to check if all the components exist or not. Because if seasonal component exists, may need to deal with the data a little different way as opposed to when the seasonal component is not present. So once you have decomposed your time series data and store it, like in the previous slide, we have stored it in the log sales time series components vector. Now this components vector contains the three components in three different variables, and the three different variables are these. So that vector contains trend variable, a seasonal variable, and a random variable, and each of these has the numbers of that specific component stored in it. So if you want to use the seasonal component, you can just take the seasonal variable corresponding to that vector and use that. And as I said, like if you have a seasonal component, there are two ways to go about it. One simple way may be to just eliminate the seasonal component. So if you subtract out the seasonal component from your time series from your original time series, then you are just left with the trend and the irregular part, and you may wish to use your forecasting algorithms just on the trend and the irregular part. And there are other ways to deal with the seasonal component. You might deal with the trend and the seasonal component the same way using certain algorithms as well. But if you just want to keep things simple and want to get rid of the seasonal component, this is what you do. You take your original time series data, or rather in our case the log transform time series data, and subtract out the seasonal part, and then in this adjusted vector on the left side we get the log transform time series without the seasonal part.